Dear student friends, we are studying partial differential equations, and last time we have studied how to form a partial differential equation from a given relation in two ways. First eliminating arbitrary constants a and b, and then eliminating arbitrary function from a given relation, how to form the partial differential equation that we have studied in last lecture. Now that means if this is a relation phi of u and v is equal to 0, and phi is arbitrary function where u and v are also functions of x, y, z, by differentiating this partially with respect to x and y, we arrived at this equation. And these are Jacobians. We denote this Jacobian by capital P, this by capital Q. P is the partial derivative of z with respect to x, small q is the partial derivative of z with respect to y, and this Jacobian is denoted by r. So equation 2 is a partial differential equation of relation 1. Now we will consider example of this, a problem on this, so that the method will be, or the procedure will be more clear. Now this is the problem. Form PDE by eliminating arbitrary function f from this equation. F of x square plus y square plus z square and z square minus 2x into y is equal to 0. Now we shall solve the problem. Here instead of phi, the function considered to be f. So whatever it may be, f or phi. But we may consider this as u and this function as v. So the given function is, or the given relation is, f of u v, f of u and v is equal to 0, where u is equal to the first function we are assuming. We are using the same notation as in the method that we have derived last time, x square plus y square plus z square, and v is z square minus 2 times xy. Now by this method directly we can get the partial differential equation corresponding to this relation as capital P into small p plus capital Q into small q is equal to r, where capital only we need to find p, q, r, and these values are given by this Jacobian. Now we have capital P is Jacobian of u and v with respect to y and z, and this we know how to express this as a Jacobian. Partial derivative of u with respect to y and z will be the first row, dou u by dou y, dou u by dou z, and second row of the determinant is partial derivative of v with respect to y and then partial derivative of v with respect to z. So easy to remember, partial derivative of v with respect to z, and these we can calculate this as partial derivative of u with respect to y. U is this function, so the partial derivative is only 2y. X and z, z are to be considered as constants, and therefore this will be, partial derivative will be 2y. And next, the partial derivative of u with respect to z, that is 2z, and in the second row partial derivative of v, that is with respect to y, and which will be minus 2x. Here u and v are functions of x, y, z, and when we differentiate this with respect to x, y or z, the other variables are to be treated as constant, and therefore here when we differentiate v partially with respect to y, we treat z and x as constant, and therefore this will be minus 2x only. So that is minus 2x, and partial derivative of v with respect to z is 2z, and expansion of this will be 4yz minus of minus becomes plus 4xz. So this is equal to 4 times y into z, and plus 4 times x into z. Or we can take 4z common and in bracket it will remain x plus y. So that is 4 times z is common and in bracket it will be x plus y. So thus we have obtained p value. Now we shall obtain q and r, and then our equation will be second equation. So what is q? It is here. Q is, so this is to be remembered in cyclic order. The numerator, the functions are u and v. The denominator changes. These are the variables y and z in the first coefficient of small p, and at denominator. And here at denominator the variables are z and x. Y, z, then z, x, and then xy in cyclic notation. See x, y, z. See if it is y, and this is z, and this is x. Then y, z, then z, x, and then xy. So in this way we have to remember the values of p, q, and r, Jacobians. So this is Jacobian of u and v with respect to z and x. And as earlier, this will be a determinant. This is determinant whose first row is dou u by dou z, dou u by dou x, and next is, so that I shall write somewhere here, dou u by dou z, dou u by dou x, and second row is dou v by dou z, dou v by dou x. This is the value of q. Now we will calculate this. Or this is equal to, see, partial derivative of u with respect to z is 2z. Partial derivative of u with respect to x is 2x. Simple to write the derivatives. And v with respect to z is again 2z, and v with respect to x is minus 2y. Expansion of this 4 is common, and it is negative 4zy, again minus 4zx, or we may have minus 4 into z common, in bracket what remains is x plus y. So this is q. Now what remains is r. R, we know it is Jacobian of u and v with respect to x and y, and this is partial derivative of u with respect to x, partial derivative of u with respect to y, and second row partial derivative of u with v with respect to x, and partial derivative of v with respect to y. Now we may see this is the determinant. It is 2x, 2y, and this is minus 2y, partial derivative of v with respect to x, and last is, that is minus 2x term here. And expansion of this determinant will be is equal to, that is r. See, minus 4x square, minus of minus becomes plus 4y square. Or if we take negative 4 common, then in bracket it will be x square minus y square. So thus we obtained the values of capital P, Q, R, and now the required partial differential equation is capital P into small p plus capital Q into small q is equal to R. Now we have to put the values of P, Q, R. Here it is P. So this value is that is 4z into x plus y times p. Q is there minus 4z into x plus y into q and is equal to r as it is minus 4 x square minus y square. Now this can be simplified, 4 can be cancelled throughout and this can be factored. X square minus y square can be factored. We know the factors are x minus y into x plus y, and then x plus y also can be cancelled throughout. So after simplifying and cancelling the factor 4 into x plus y, it remains z into small p minus z into small q is equal to minus x minus y will remain here, or x plus y is throughout cancelled, 4 is also throughout cancelled, or that can also be written as z into p plus q and plus x minus y is equal to 0. So this is required PDE. So in this way we can use the method of elimination of arbitrary function to obtain partial differential equation. This is the required PDE of relation 1, this relation or the given relation. So this is the partial differential equation of this equation, and here f is there. We have eliminated f and we have obtained the equation in terms of x, y, z and small p and small q, which are the partial derivatives of z with respect to x and y. Now this equation we will study further. So that is the equation capital P into small p plus capital Q into small q is equal to r. This is an important equation in partial differential equation, which is known as Lagrange's linear partial differential equation. Lagrange's linear partial differential equation of first order. The equation is called the Lagrange's linear PDE of order 1, where these capital P, Q, R are functions. We have obtained here, you see, Q is function of x, y, z, R is also function of x, y, z and P is also function of x, y, z in earlier example. So where P, Q, R are functions of x, y, z. And we know this is a partial differential equation of the relation phi of u and v is equal to 0. So this we have studied earlier. We know that this equation 1, PDE 1 is the PDE or partial differential equation is the PDE of the relation 1 of the relation is phi of u and v is equal to 0. So we have proved this as this elimination of phi function from this relation gives this as the partial differential equation. So therefore now what is the relation between the partial differential equation and its solution? Now see, this is PDE, 1 is PDE of this equation, and again in turn this equation is called solution of the partial differential equation 1. So therefore this is, so phi of u, this equation or this relation, phi of u and v is equal to 0 is the integral or solution of equation 1. So because from eliminating the arbitrary function phi, we obtain the PDE. The relation or the function phi of u and v is equal to 0 is the solution. Is the solution, or it may be called integral, solution integral of the PDE 1. Now where u and v are to be find out, and we will suppose u and v are, how to find u and v, that we shall consider. So this is the solution of PDE 1, that is to be noted. So relation between these two, this is the PDE of this equation, and this equation is the solution of PDE 1. Now let u is equal to C1 and v is equal to C2 be two functions. Be two functions whose partial differential equation we shall find out. Whose PDE we shall find. Now because C1, C2 are constants to be considered here, and differentiate this, differentiating this or taking differential, total differential of this. So we will get of u is equal to C1 and v is equal to C2. We have, see, the differential of u is du. We have studied earlier differential of u, du, and differential of constant is 0. So du is equal to 0, and similarly dv is equal to 0. But what is du? U is function of x, y, z, and therefore we have to differentiate this, and with respect to x, y, z, and take the corresponding differential. So that means du will be dou u by dou x into dx, partial derivative of u with respect to x into differential of x plus. So this relation is for the total differential. So we know it that if z is a function of x, y, z, then dz is dou f by dou x into dx plus dou f by dou y into dy, etc. And similarly here du will be, total differential of u will be partial derivative of u with respect to x into dx. Similarly, next part will be partial derivative of u with respect to y into dy, and partial derivative of u with respect to z into dz is equal to 0. And what about dv? dv will be similar to this, dou v by dou x into dx plus partial derivative of v with respect to y into dy plus partial derivative of v with respect to z into dz is equal to 0. Now we solve these two equations for dx, dy and dz. So solving these, for dx, dy, dz by Cramer's rule, we have dx divided by, now you see corresponding determinant. So see, hide this column, and then the coefficients of dy, dz from remaining is to be written in the form of determinant. that is dou u by dou y and dou u by dou z. Second row, dou v by, hiding this, dou v by dou y, and next is dou v by dou z. Partial derivatives of this. This is equal to dy. For dy there is negative sign, and if you hide this part, then we will write this as the first column of the determinant. That will be dou u by dou z, and this is dou. Then this we will write partial derivative of u with respect to x, and then second row will be partial derivative of v with respect to z and partial derivative of v with respect to x. So this is the second term, and this is equal to dz divided by, and hide this part, and then the coefficients of dx and dy are to be written in the determinant. That is, first row is this dou u by dou x and dou u by dou y, and second row partial derivative of v with respect to x, partial derivative of v with respect to y. And we see these are exactly the values of capital P, capital Q and capital R. Earlier we have seen, you may refer the earlier part and check it. That is, this is dx upon capital P is equal to dy upon capital Q is equal to dz upon capital R. And if we suppose this as equation 2, then this is the equation whose solution is, so this is the equation corresponding to these two functions, and this is the partial differential equation of u is equal to c1 and v is equal to c2. What we have written here, the two functions whose PDE we shall find out, and this is the PDE. So this is the PDE of u is equal to c1 and v is equal to c2. So thus this is the PDE of u is c1 and v is c2. That means we have obtained u and v, and now we know this is the relation phi of u comma v is equal to 0 and is the solution of partial differential equation 1, and thus these equations, so these functions give the complete integral or general integral as phi of uv, general integral of PDE 1. General integral phi of u and v is equal to 0 of the PDE 1. 1 means of the PDE capital P into small p, capital Q into small q is equal to r, and thus the solution of this differential equation is obtained, because we know the solution of this differential equation is of this form, phi of u comma v is equal to 0, or phi of u and v is equal to 0, and where u and v are to be find out, and we have find out u and v as solution of the second equation. And thus if you consider this equation is to be considered for solving Lagrange's linear equation, or therefore the equation 2 is called Lagrange's auxiliary equation. So the equations 2 Lagrange's auxiliary equations or subsidiary equations. equations of and thus what is the method or working rule to obtain or to solve this equation is we will write in short. So working rule to solve the Lagrange's linear equation, that is this equation. We write the auxiliary equation. Auxiliary equations. And after writing these auxiliary equations, we solve these equations and let u is equal to c1 and v is equal to c2 be the solution of these equations, auxiliary equations. Let solving this, let u is equal to c1 and v is equal to c2 be the integrals of it. Then the general integrals of suppose, or you may suppose this as 2 and this as 1. The general integrals of 2. We have to, this is the original equation, and from this original equation write the auxiliary equation and solve this, and after solving this we will get these two integrals, u is equal to c1 and v is equal to c2 with the integrals of 2, and then the general integral of 1 is given by phi of u and v is equal to 0, or that can be written as u is function of v. So this is the general integral of the Lagrange's linear partial differential equation of order 1. So thus we have written the method to solve Lagrange's partial differential equation. And first the equation is to be written. Note the values of p, q, r. Write these equations, simultaneous equations, and these equations can be solved by, we have written only solving this, but how to solve that will be explained in solving the problems. We have to use the method of grouping. Take these two ratios, solve it, find one solution, and in the second part take another two ratios which are convenient, that are to be decided by observation, or we have to use the method of multipliers. Now that method we will discuss in our next lecture. Thank you.